Morning, everyone. So this class, let's continue on the final part of the single particle dynamics. Okay, so it has been quite a long time because last time we talked about this was last Friday. So we introduced quite a lot of equations in there. So this class, we're going to start from there. Okay, so let's do a quick recap because we really want to understand this drag force here. Okay, so if we talk about the drag force, so there are basically several forms of this force. So drag force exists whenever there is relative velocity. So as long as let's say the particle velocity is not equal to the fluid velocity, you will have drag force. But if they're the same, then there's no drag force. Just remember that problem we talked about. If we have a flow going by, right, and then if there's a particle that's flowing with the same speed of the flow, then the drag force is equal to 0, right? Only when there is relative velocity, there's drag force. So we started the drag force equation with the Newton's form. So that will give you FD equal to CD AP rho F VR squared divided by 2. Okay. So then we introduced that basically CD is a function of the Reynolds number. So when it's in laminar regime or when it's in Stokes regime, it has a simplified form. But when it's in the other regime, there are more complicated equations, just like the equation that you used to calculate, I think, one of the homework problem, right? So you have to use a more complicated equation to consider higher Reynolds number situations. So basically, if we divide these scenarios, so we have the high Reynolds number. If Reynolds number is larger than 0.1, then remember that graph where the CD is a function of Reynolds number. You have this straight part here, and then you have something here. So basically, we're talking about this regime. Then you have to plug in the actual number of CD or use some more complicated equation to calculate the drag force. But when it's in the laminar regime, or Reynolds number below 0.1, call this laminar regime or Stokes regime. There's a more simplified equation, okay? So that's the equation that I wanted all of you to memorize, okay? So I'll show this pool here. So which equation is it? So try to look at your previous class notes as well, okay? So if you don't remember it, take a look. Okay, 10 more seconds. Okay, we'll stop here. All right, so I would say most of you are correct. That's 3 pi mu dp multiplied by VR divided by C. Okay. 3 pi mu dp VR divided by C. Okay, so this is the equation that I want all of you to memorize. Okay, so I said that there's not a lot of requirements from this class. Okay, but please know this equation because we're going to use that for a lot of the analysis in the particle removal devices, particle control devices. Okay, so in this equation, the mu here is the viscosity, the air viscosity, right? It's typically in the range of 1.7 or 1.8 multiplied by 10 to the negative 5. If we use standard units, okay, I think it's kilogram per meter per second. Okay, and the dP here is the particle size. It's in meter or particle diameter, right? So VR is the relative velocity. And C here is the Cunningham correction factor. So further, we know that the Cunningham correction factor is basically a function of the particle size and the mean free path. So I think you guys worked on some problems for solving this Cunningham correction factor and then calculate the drag force. Okay, so we'll stop sharing the pool results. And so we mentioned that basically this C here satisfies a relationship. Basically, if let's say the particle size is much larger than the mean free path, right? Then C is equal to 1, or it's very closely equal to 1. This much larger sign just means that dP is dP is probably larger than 100 times of lambda, right? But when dP is comparable, or it's not much larger, let's say, not much larger than lambda, we have to plug in this equation. And then to calculate what is the actual drag force, right? So basically this C here, I'll just repeat the equations. It's also in your textbook, okay? dP 1.257 right? So we can use this equation to calculate the Cunningham factor, correction factor, then back calculate what is the actual drag force. So this is what we have gone through from our previous classes. And with the drag force, we introduced an idea that's about the free settling of a particle, right? So whenever we talk about the particle settling, we have force analysis, right? There's going to be gravity making the particle to settle down, and the drag force to balance it. So we introduced an idea that's called the terminal velocity, or the terminal settling velocity. So you don't have to memorize the equation for this one, because we can always equate the drag force with the gravity, right? 3 pi mu dP Vt divided by C. This Vt is the terminal velocity, right? By equating these two, we can calculate what is the terminal velocity, right? So particles with different sizes, they're going to settle with different speed. So last class, I asked you, basically for the class on Monday, I asked you to watch a video, basically about the about the SARS-CoV-2, how we can understand this transmission from the aerosol perspective or particle perspective. So if you remember in the part 2 of the lecture that's given by Professor Lindsay Marr, she gave this equation, she gave this plot here, right? So if you still have the impression there, this is the settling velocity, okay? So basically, if we want to understand how long these respiratory droplets, right, these saliva droplets, or cough droplets suspend in the air, we have to consider the free settling velocity of these particles. So unfortunately, you see that for these particles, for them to settle down 1.5 meter, which is in general the height of the mouse, okay, the average height of people's mouth, right? After particles are emitted, it's going to free settle onto the ground. So unfortunately, you can see that people use the 5 micrometer as the boundary between droplets and aerosols. But you can see that 5 micron particles, they're going to take almost 30 minutes. They're going to take 30 minutes to settle down, right? And we were using a social distancing of 6 feet or 2 meters. So it's highly unlikely that the social distancing or the space is enough, right? So basically it means that these droplets can still be airborne because they can still suspend in the air for a very long time. So that's why wearing masks will be very important, because if you just keep the distancing, then the particles can still, or the viruses can still suspend in the air. So if we wear masks, then we can effectively block these droplets, right? So she also mentioned something about the evaporation of these particles. So the situation is that each droplet, let's say cough droplet, during speaking, those droplets are mostly composed of water. So I think it's more than 95% of the composition is just water. So we know that once we emit a water droplet into the air, it's going to quickly evaporate, right? So this further, I would say, worsen the case, right? Because let's say originally we emitted 5 micron droplets into the air. And then because of the evaporation, it quickly evaporates, right? So basically the size will shrink to the smaller side, right? If they shrink to the smaller side, then they're going to suspend for even longer time. So we have to also consider how the particle size evolves. So basically this figure shows you under different relative velocity. Let's say for indoor condition, we know that our building HVAC is going to control the RH to somewhere around 50%, right? I think it's probably 40 to 60%. This is the typical indoor RH. Okay, so what this means is that, let's say if we have a 5 micron particle in the beginning, then it's going to quickly shrink to around 0.4 times of the original size. This is final divided by initial diameter. So this 5 micron particle is going to shrink because of evaporation to around 2 micron. Okay, if you look at 2 microns, you can't even find what is the terminal velocity because that's too long. Well, that's the settling time is just too long. So we're adding in this aerosol perspective so that people can know that there are extra methods to contain this virus or to reduce the transmission of the virus, right? So for this class, we're going to basically build upon these equations we have and try to understand the transient movement of these particles. Okay, it's going to get a little more complicated because we need to solve a few differential equations, but I'll just demonstrate these procedures in the class. Okay, so we mentioned about terminal velocity. So basically, terminal velocity is a velocity when the drag force balance with the gravity, right? But this is not always the case because let's say if we release a particle at a certain height, right? For example, coughing, when we directly emit these droplets, they don't have a vertical velocity. So what happens is the drag force is going to gradually build up, right? Until the velocity is high enough so that the drag force is large enough to balance with the gravity. So basically, if we show this velocity as a function of time, let's say settling velocity, which is the vertical velocity going down, initially it's going to be 0 because there's no vertical velocity going on. So as time goes on, the velocity will become larger, and then finally it reach to a a steady state velocity, because at this time, the drag force basically balanced with the gravity, right? But what about this period? So can we characterize this period? For example, how long is this period? Let's say if we talk regard this period as t0. So how long is t0? Is it going to take a year for the particle to reach to the terminal velocity? If that's the case, we don't even need to consider this terminal velocity, because it's never going to reach to steady state. So is it going to take a second to reach to steady state, right? So this is where we have to consider the transient property, basically to use some differential equation to understand this process, right? So let's build up this equation again. So according to the Newton's second law, right, the MA is equal to all the forces on the particles, right? So that's going to be mg divided by the drag force. Drag force is 3 pi mu dp multiplied by v divided by c, okay? Because the air here, we assume is stagnant air. So the air doesn't have any velocity. So because of that, the relative velocity is just the particle velocity, right? So we also have the A here. We can plug in A as dv dt equal to mg minus 3 pi mu dp v divided by c, okay? So this is going to be a differential equation that's based on v here, because all the others are just constants, right? So let's do another change here, right? We need to divide m on both sides. So we have dv dt equal to g minus 3 pi mu dp divided by c. Let's put our velocity outside, okay? And then we have m is just pi over 6 dp squared and multiply dp to the third multiplied by rho particle, okay, which is the density of the particle. All right, so this is going to be equal to g minus 18 mu dp squared rho p c multiplied by v. Okay, so this is how we can transform this equation so that it has this type of form. It's a little bit more simplified. So if we look at this term here, so of course the gravity is going to be a constant, right? The mu, particle size, the particle density, and c, they're all constants, right? Especially particle size. It's not like when you settle down, the particle shrink or increase, right? Expand. So what we can do is we can set this term as b, okay? It's going to be a little bit easier when we derive the equation. So now we have dv dt equal to g minus bv, okay? So I don't know, when did you guys learn the calculus? I guess it's probably freshman or sophomore, but if you still have this skill, let's try to spend some time solving this differential equation, okay? So I have a pool here. So what's going to be the solution for this differential equation? Let's take maybe 2 minutes. You can either integrate it or you can differentiate the answers, okay? Take a look. So some of you are really quick, okay? So actually, I just realized that you can use another approach to look at this. Okay, so consider when time is equal to 0, what is the velocity? It's 0, right? And when time is equal to infinity, then it's going to have a settling velocity. So try to take a look which one satisfies this. Okay, 10 more seconds. All right, we'll stop here. Okay. So the one that got the most answer, that's correct. Okay. So I was mentioning that you can quickly try something different, right? You don't really have to integrate or differentiate. So at time equal to 0, it should be equal to 0. So if you plug in t equal to 0, then the exponential term here will be 1, right? So 1 minus 1, that's going to be 0, velocity equal to 0. But if you plug in time equal to 0 to the other two options, so that those won't be equal to 0. But here, theoretically, we should derive this equation in a more rigorous way, okay? So I'll just show this process just in case that some of you are not familiar or forget about this this calculus section, all right? So basically what we can do is we can first substitute something, right? So what we can do is we can further make this equation a little bit longer, right? So make it g multiplied by, or it's actually minus b multiplied by v minus g divided by b, okay? It's still the same compared to the original equation here. And now what we can do is we can substitute this capital Y. Let's define a new parameter, which is v minus g divided by b. Okay, so with this definition, with this new definition, you can see that the dv dt is going to just be equal to dy dt. Mainly because g over b, that's a constant, so it's not going to contribute to this derivative here. But on the right-hand side, you have b multiplied by y. Okay, so now if you have this equation, it's going to be easier for you to calculate. So directly, so y should be equal to y0 exponential minus b, minus bt, basically. Okay, so I guess this is something you can memorize after doing enough integration problems. But really, the detailed process, I can just also show that as here. So you have dy divided by y equal to minus b dt. Okay, so if you integrate on both sides, you have log y equal to minus bt plus c. Okay, so basically you integrate on both sides. Log y, the derivative log y is going to be 1 over y, right? So then you have y equal to exponential minus bt plus c. We know that exponential, one term plus the other term is going to be equal to the multiplication of these two terms, right? This exponential c, you can just regard it as y0. Okay, so this is how we can get into this step, right? And then we mentioned that we have to look at the initial condition to try to solve what is the actual y value here. So we mentioned that at initial condition, which is time equal to 0, then velocity is equal to 0, right? So because of that, then y should be equal to minus g over b, right? So if you use this condition and then plug in here, so basically you should have minus g over b equal to y0 exponential 0, right? This is going to be y0. So now we have y equal to minus g over b exponential minus bt. And then we can further plug in this definition here, because we know that y is equal to v minus g over b, right? So b, finally, that's going to be g over b, 1 minus exponential minus bt. Okay? So this is how we solve this differential equation by using the initial conditions there. All right? Any questions? I hope this is not too complicated. All right? So now we have the expression of this terminal velocity, right? And then further we know, remember here, we made this substitution, this b here, okay? So let's just write this equation here again. So b is equal to g over b, 1 minus exponential minus bt, right, in the bracket, right? So one thing we can find out, so right now we just plug in t equal to 0, we solve this entire equation, right? And then one thing we might be interested in is what's going to be the velocity when t is equal to infinity. Okay, so when t is infinite long, what's going to be the velocity there? So we can easily plug that in. You can find out that, so if t is equal to infinity, this term is going to be equal to 0, right? So then we're just going to have g over b. And then if we plug in the b term here in the beginning, we're going to have g dp squared p c divided by 18 mu. So this looks a little bit familiar, right? This is just the settling velocity or the terminal velocity. So this is just the terminal settling velocity that we talked about at the beginning, right? And this makes sense. The terminal means time equal to infinity, right? This thing makes sense. So now we can really use this equation to draw out what the settling velocity looks like. So if this is on the axis, x-axis is time, y-axis it's a settling velocity. So we know that at the beginning, the particle velocity will be 0, and then it's going to follow this exponential term. Then it's going to look like something like this, okay? So we know that it's the terminal velocity, and here is 0. So let's go back to our original question, right? We were interested in what's going to be this time. So how fast is this, right? We were mentioning if this time period is in the time scale of years, then basically we don't need to worry about this terminal velocity. Why do we still need that? Because it's always in this transient form, right? But if it's in a few seconds, then we can say that, well, the particles quickly reach to its terminal velocity, right? So this time here is basically going to be dependent on this exponential term here. So if you look at this term here, okay, what we can do is we can do another substitution. Let's assume that tau is equal to 1 over b. Okay, so this thing can change to this equation here, or the settling velocity can change to another term. So we're just going to have g tau, and then 1 minus exponential minus t over tau. Okay, so this is a substitution we make. So the relative length of this time is just dependent on this tau here. The reason why I use substitute this term as tau is mainly because this term has a unit of second. Okay, because you see this is time divided by tau here. So tau had to represent something that's related to time. And if you look at this term here, so g minus tau, it's just acceleration multiplied by time. So that's why you got velocity, right? So all the units make sense here, right? So the relative length of this time is just dependent on tau here. So what is tau? So we have b equal to this whole term here, right? Tau is just the reverse of this term. Right? We have tau equal to dp squared rho pc divided by 18 mu. Okay, so to confirm that our thought is correct, which means that this tau is the time, it's a term that's related with time. Let's just quickly substitute the units here. So you have dp, which is in meters, right? Meter square, right? Rho p, you have kilogram per meter square, a meter cubed. And then we know that c, the Cunningham correction factor, is unitless, right? And on the in the denominator here, that's going to be kilogram per meter per second. Okay, so we can cancel quite a lot of terms here. So kilograms canceled, right? And this is going to give you 1 over meter. But this whole term is going to carry a unit of second, right? So basically, we simplify this terminal velocity, or the transient terminal velocity, into a exponential term here, right? And we know that now this the time that's needed for the particle to reach to the terminal velocity is totally dependent on this tau. We actually call this tau as the characteristic time. So it's totally dependent on the particle property. Okay? Of course, it depends on the fluid property as well, because viscosity is dependent on fluid velocity, but it's largely dependent on the particle properties here. And more specifically, it depends on the particle inertia. So basically, if the particle have a larger inertia, let's say it's more heavy, right? Larger in terms of size, then the characteristic time will be longer. So what that means is that it's going to take a longer time for the particle to reach to this terminal velocity here. Okay, so we can quickly plug in a few values. So let's say when time is equal to 1 tau, 1 multiplied by tau. So we can find out that we can basically plug in the time here, right, equal to tau here, right? So we can find out that this is just tau 1 minus exponential of -1. Okay, time equal to 1 tau. You have -1 here, right? And this term is equal to 0.63 g tau. Okay, so basically what that means is that at time equal to 1 tau, it's already at this point. So it's 0.63 of the terminal velocity, right? The g tau is the terminal velocity, which is this term here, G over B, right? That's G tau. Okay, 0.63 of the terminal velocity. And when time is equal to 3 tau, then V is going to be G tau 1 minus exponential minus 3, right? And then we have actually 0.95 G tau, which means 0.95 VT. Okay, so when time is equal to 3 times of this characteristic time, then the velocity reached to around 95% of the terminal velocity. Okay, so this characteristic time really determines how fast the particle reached to its steady state, right? Then how large is this, or how long is this characteristic time? So we can find out, basically, if we plug in particles with different sizes, let's say when the particle size is equal to 1 micrometer, we can basically plug in these conditions, right? Assuming it has water density using the air viscosity, we can find out that this characteristic time is very short. That's 10 to the minus 5 seconds. Okay. What that means is that if we release a 1 micrometer particle in the air, it's going to reach to steady state, reach to the terminal velocity very quickly. Okay, around 10 microseconds. But when the particle size is equal to 1 millimeter, which is kind of like a small bead or grain of sand, right? Then this tau here is 10 seconds. Which means that if we release that particle, release that sand particle there, then it's going to take 10 seconds for it to reach to the steady state or the terminal velocity. Okay, so you can really see that basically particles with different sizes is going to affect how fast it reaches to the steady state. But as I mentioned, in this class, we're mainly dealing with smaller sized particles, right? Particles of around 1 micrometer or below 1 micrometer, right? Because those are the suspended particles, right? What that means is that they're just going to quickly follow the ambient flow, right? So it's going to quickly reach to the steady state where it's just going to go with the flow, right? So this is about the settling velocity, which is in the horizontal direction, which is in the vertical direction. So we can also analyze the situation when the particle travels in the horizontal direction. So let's say that we can inject a particle with the initial velocity. Let's say, assume that this initial velocity is u0, okay? And then it's injected into a stagnant air, where the air doesn't have any velocity. So because of that, the particle will endure a drag force that's pulling it this way, right? So we can also analyze the movement of the particle in the horizontal direction. So what happens is basically we can still set up the Newton's second law, right? And dV dt, which is ma, equal to minus fd, right? And then basically we have dV divided by dt equal to minus 3 pi mu dp divided by c, and then divide by this mass, okay? And then multiply by the relative velocity, basically the velocity of the particle. So what we can have is dV dt equal to minus 18 mu dp squared rho pc multiplied by v, okay? So if you remember the definition of the tau earlier, so basically it's the same as the term here, right? So what we can do is just set this term as v divided by tau, okay? So for this differential equation, it's going to be easier compared to that one, because for this one, we have to substitute this whole term as y. So finally, we got a term that looks like this, okay? But for this equation is directly simplified into this form. So we can directly solve for the velocity v here. So the v is basically, let's say, it's going to have u0 exponential minus t divided by tau. Okay, this is because when time is equal to 0, the velocity is equal to u0, right? And then because of that, we're going to also have an exponential term. So what this means is that if we plot out the particle velocity as a function of time, then it's just going to decrease exponentially until it reaches to 0. Well, it's never going to reach to 0, right? Because if we plug in, even for time equal to infinity, let's say if the limit of this term is going to be equal to 0, but it's never going to touch this. It's never going to be equal to 0, right? It's just going to decrease exponentially, right? So although the time won't be equal to 0, or the velocity won't reach to 0, but we can also calculate the maximum distance that it can travel, right? The distance is not going to increase infinitely. So we can just integrate this velocity as a function of time from 0 to infinity and calculate what is the distance or the maximum distance that it can travel. Right? We'll just integrate from 0 to infinity, and you can find out that this distance is just u0 multiplied by tau. Okay, so now you see it is actually quite convenient if we define this this characteristic time here, because it's similar to the typical movement of any object, right? So if we know a time, we just multiply that by the velocity to get distance, right? If we know the let's say if we know the characteristic time, we just need to multiply that by the basically by the acceleration, right? So we can get the terminal velocity, right? So this is the equation or the derivation for the horizontal movement. So you can see that basically for particles with different sizes, they're also going to have different maximum distance. So let's say if we look at this problem again, particles with size of 1 micrometer and with a size of 1 millimeter, then because their characteristic time differ by 6 orders of magnitude, their maximum distance in the horizontal direction is also going to differ by 6 orders of magnitude, right? So what this means is that if we inject particles at the same speed into a stagnant air, then smaller particles will quickly, so basically their distance that can be traveled will be very short compared to a larger particle that's injected at the same speed. So that's why these submicron particles, they can suspend in the air for a very long time, right? So they cannot, their velocity will quickly reach to the ambient velocity, right? And also their distance that can be traveled is also very short, right? Because, for example, 1 micrometer particle, we have an initial velocity of 10 meters per second. Then the distance that they can travel is just 10 to the minus 4 meters, right? Which is negligible. Even our bare eyes cannot tell this difference, right? So that's why these very small particles, they can suspend in the air for a very long time, okay? So basically, this is all about the particle dynamics. So at the end, in this class, we introduced the differential equations to understand the unsteady state condition, right, for the particle movement. And we were trying to understand this specific time here because it matters a lot for the particle movement, and also it matters a lot for the particle removal, right? So let's say if we want to design a system, we want to design a duct, right? And we just want the particles to settle down onto the bottom to remove these particles just by pure gravity. Then we have to design the duct that's long enough so that the travel time of these particles is much, much larger than the characteristic time, right? Because otherwise, if it's similar, then these particles won't even be able to move a lot, right? So this is related to the design of these particle removal devices. Okay, so finally, I want to quickly introduce the next few chapters or the classes that we are going to go through. Okay, so here we already understand the drag force and the particle movement. So now we're going to apply these ideas into different types of particle control devices. So we're going to talk about the gravitational settler. Gravitational settler. Okay, we're going to talk about the cyclones, electrostatic precipitator, Baghouse filter, and finally the wet scrubber. So we're going to take either one or two classes to talk about these removal devices. And then we'll also do some calculations here. So a lot of them, you can just tell the mechanism by their names, right? The gravitational settler is just this duct here. You want to remove the particles by settling them down, right? So the cyclones is using the similar mechanism of for example, the tornado or the hurricanes, right? So the cyclones are basically these rotational movement of the airflow, right? So we know that the larger particles, they're going to need a higher centrifugal force to maintain them to rotate there, right? So they have to balance with a drag force, but if the two forces cannot balance, then these particles will just spin, will be spinned to the outside, right? And then if we have a collector that has a shape like this, then the particles can get collected onto the wall and then finally get removed at the bottom, right? So the electrostatic precipitator uses the electrostatic force. It's similar to the device that we talked about last class, which is using the electrostatic force to classify particles. Basically, we use this extra force to collect them onto certain plates or certain wires. So Baghouse filter, right? I believe that quite many of you have filters at home. Probably need to install the filter yourself as well. So the filter will collect the particles by the physical mechanism where the particle is too large, it's going to get blocked, but also by the electrostatic force that we introduced here. Okay, so the wet scrubber is similar to a cyclone, except that we will inject water inside. So if we spray water, then they're going to collect the extra particles that's in the gas stream, so we can achieve the PM control. Okay, so in the next few weeks, we're going to focus on these devices, and then you can also realize how our drag force, again, 3 pi mu dp v divided by c. Okay, you can find out how this drag force are playing a role in these devices. All right. So that's all for this class. Feel free to let me know if you have any questions. All right.